All right, so we're going to kick off, and thanks for that kind introduction. I think we've got a bit of a technical hitch, not surprising when it comes to TB. It's never straightforward. A couple of sort of housekeeping announcements. We'll keep it fairly informal. There are two parts to this course. The second one is tomorrow. If for those of you not familiar with that, so it's a two-part course. The first part's today and the second part's tomorrow. The one we'll deal with today will deal mainly with the history of TB and the different cycles and stages of TB. It's quite a complex infection and a bug, as some of you may know already. And tomorrow we'll deal more with prevention and treatment. Yes, go ahead. Do I? I have one mic here. What do you mean, do I have a microphone somewhere?
It wasn't working this morning, so...
Oh. Well, it's working now, I can assure you. Yeah. Hey? Is there a problem here? Are you referring to the echo, or in terms of magnitude of sound you can't hear? Is it okay? Well, I'm just asking the lady here who... Okay, great. Okay. So please, if you need any clarification, stop me. There's a couple of ways we can do it. We can take most of the questions tomorrow. But if you need any points of clarification, please stop me. And the idea is tomorrow to keep the lecture much shorter. And then we can talk a lot about TB and any points of clarification that are required. So let's just get a feel for who's here. How many of you are from a medical background? Please pick up your hand. Okay. What about from a scientific background? Okay. All right. Anyone else here based in other fields, arts, humanities, law? No. Okay. Oh, somebody. Okay. All right. So let's get going. And I've put in a lot more slides than we're going to go through in detail. And that's more because you get a copy of these slides, okay? And so you can always refer to them. So I like to put in more detail. And I'm not going to go through every slide, and I'm not going to go through every line of every slide. But I think what this constitutes is an information pack of slides that you can use and refer to in the future. So you are going to get a copy of all the slides. So there's no need to feverishly write notes. Now, I just put in this slide because here we can see some very opulent sides of Cape Town. But of course, there's a much darker side of Cape Town, and where much of the population lives and where TB thrives in the informal settlements and slums in the Cape Flats. And here you can see many famous people who had tuberculosis, including Nelson Mandela, Bishop Desmond Tutu, his Mother Teresa, and I don't know if some of you may recognize that chap. He's a very famous Indian actor in the Bollywood movie scene. And the reason I put it in that little insert is that India has the highest burden of tuberculosis globally in terms of sheer numbers. It contributes almost a third of TB cases globally. And I think at this juncture it's useful to remind ourselves of the words of a very famous British physician. Some of you may have heard his name before, William Osler. And these words, just to give you some context, were said in sort of at a time when the TB rates in London were roughly what the TB rates are currently like in Khayelitsha, extremely high. Almost 1 to 2% of the population of London had active tuberculosis, and the death rates were extremely high. And he said in the mortality bills, pneumonia is an easy second to TB. Indeed, in many cities, the death rate is now higher and has become, to use the phrase of Bunyan. Bunyan was another physician, and he had christened pneumonia the captain of the men of death. And so William Osler is saying, no, it's not pneumonia, It's actually TB, which in a way is a form of pneumonia, but it's more chronic. And this situation, unfortunately, is the situation we find ourselves in today, where in this country, TB is now the commonest cause of death by any standard, even surpasses motor vehicle accidents, traumatic causes of death. And it's a foremost infectious disease killer globally. So in a way, in terms of context and time, these words are very apt today as they were in London at the turn of the last century. And here, just to show you some pictures to remind ourselves that the biggest driver of TB is poverty and overcrowding. And the other little inset I put in was just to show you that it's not only a problem in South Africa or in Africa. In fact, that's a queue of migrants waiting to enter Europe. Germany last year had over 1 million migrants. The European region, which includes Russia, has the highest absolute number of drug-resistant TB cases diagnosed annually. There's been a resurgence of TB in Europe. In the UK, the rates of TB are now the highest than they ever were before, in the last couple of decades. Big burden of TB in India, in China, and many other parts of the world, but certainly not a major Western European or US problem. So this is just to give you an overview of the different aspects that we'll address during this lecture. As I said, I will flip through some of the slides. It's more there for your information, and I will only highlight certain points. And these are the main things I will cover. What is TB? How did it evolve? I think given the nature of the audience, I won't spend too much of time on that. Why is this an important disease to talk about? I mean, there are hundreds of diseases out there. Why do we really need to worry about TB of all things? What's the historical? I've covered some of the history, but how has this changed over the centuries? What are the key drivers of TB? And why do we have so much of TB in South Africa? What's the life cycle? What's our most up-to-date understanding of the life cycle of TB? And how is TB spread? We all know it's spread by coughing, but how does it really spread, and how do these bugs survive the environment? And why is it that some people contract it and others don't? Why do some people get TB and others don't? I'm sure all of you know somebody who's had TB, right? Anyone here doesn't know someone who had TB? Pick up your hands. You do or you don't? Do know someone who has TB. Okay. Right, good. And then finally, how do we detect TB and what are the drawbacks? Now, if we don't get through the last one, how we detect TB, don't worry because we'll cover it tomorrow. And I'm a little bit worried with the time constraints. We may not get to that one, but that's fine because as I told you, tomorrow's content is much shorter. And so much less, and we can cover that tomorrow. Okay. All right, so TB, as some of you will know, is a bacterium or a bug. And here you can see a picture of it here, what it looks like under the microscope. And roughly the size is about 1 by 5 microns. A micron is 1,000th of a meter. So it's quite a small bug. But what makes it unique and separates it from other bugs is that it has a very thick, waxy wall, okay? And that's what makes it takes up certain stains, which gives it unique properties. It's a fairly slow-growing bug. Generally, when you look at bugs where food spoils, for example, those bugs tend to divide usually within 30 to 60 minutes is one division, right? They multiply every hour. The doubling rate of TB by microbiological standards is fairly slow, doubling rate every 24 hours roughly, okay? So it's a very slow-growing bug. It's a very fastidious bug, and it doesn't grow anywhere or grow very easily. I'll talk a bit more about that. This is just a broad classification, and the TB bug falls within a genus of bugs called the mycobacteria, okay? And the mycobacteria are the special group that I referred to, and they're all sorts of different strains. So this just gives you a rough classification of these species. The mycobacteria mycobacterial species there are almost about 150 or 160 different species described. We probably haven't described all of them, so there are probably many more. They're mainly found in soil and water, and they're these slow-growing bugs. And it just turns out that the only natural reservoir for tuberculosis is in fact man. Okay, and there are interrelated strains. The main strain which we encounter in clinical practice is Mycobacterium tuberculosis, and as I said, the only natural reservoir is humans. There is a form of TB. It's a slightly different strain. Over time, mutations have occurred, and these strains have lost certain genes as they evolved over time. And a very closely related strain called Mycobacterium bovis, affects cattle, and even lions can get TB. So when we use the term TB in a broad sense, we're talking about different strains, and Mycobacterium bovis can also affect humans. And this is a predominant form of TB when people drink infected milk. But clinically it's indistinguishable from TB, from Mycobacterium tuberculosis, and therefore we refer to this as a complex. When we talk about the causative agent of TB, we call it MTB complex, because it's actually a number of different strains that will give you a disease with the same clinical presentation. There are closely related strains that will affect, for example, fish and dolphins, but will not generally affect humans, though in people who own fish tanks, they can develop ulcers on the skin due to a bug called Mycobacterium marinum. But that doesn't give you the typical disease affecting the lungs. And then, of course, there are strains that will only affect birds, so-called bird TB, and it can affect humans under certain circumstances when the immunity is compromised, for example, in advanced HIV or in extreme old age where there's damaged lungs. One can contract these kind of strains. So that just gives you some context of mycobacteria and tuberculosis. Now, how did this come about? So in fact, these mycobacteria were prevalent on the planet for millions of years, and in fact, they co-evolved with early man and prehistoric man. And the modern members of this Mycobacterium tuberculosis complex that I'm talking about now probably evolved from a common ancestor about 15 to 20,000 years ago. And this just shows you a map where we think that it probably originated somewhere in Africa, and which is the prevailing theory, not the only theory, but the prevailing theory about where man originated and how man in fact crossed over into Europe, and with modern man evolved and spread this Mycobacterium tuberculosis complex. And then, of course, as this happened over time, slightly different strains developed and those spread. So that's currently based on archival evidence of TB and genetic sequencing, how we think things panned out. What about more recently, in the last several thousand years? TB was first described in the Rigveda by the Hindus or people in the Indus River Valley about 6,000 years ago. We know from, they called it Jayashma. We know it was present from a number of detailed written accounts, though we don't have mummified remains to prove that. And of course, going back to the Egyptian mummies, we know that TB existed about 5,000 years ago. There's also evidence in mummies from the Andes. And so we know that TB was already present all over the world. It was present in Africa, and it was present in South America at low levels. And we're not sure, perhaps it crested at some time a couple of thousand years ago and then receded. But we do know that by the time TB was exported from Europe, where it later became endemic to the rest of the world, at that time in Africa and certainly China and the Indian subcontinent and South America, TB had receded. It was well described by the Greek scholars, and as I said, there's archaeological evidence from medieval times from many European cities. TB really played it was very low key globally. And then with increasing urbanization in Europe from around about the 15th century onwards, the TB rates skyrocketed in Europe. We know there was a really high burden of tuberculosis in that part of the world. And I referred to Sir William Osler's words, and I talked about the very high rates in London. And the epidemic peaked in Europe and North America in the 18th and 19th centuries, and many of you may have had ancestors or been told about relatives, your grandfathers or great-grandfathers who had tuberculosis. And during this time, of course, subsequently came the era of colonization and European nations claiming ownership or rediscovering, as I like to call it, many lands that were already thriving. And TB spread to many areas where it was previously non-existent or eradicated. And so there are a number of examples in Alaska, in South America, in North America, where there were people from Europe who first went to these areas and, for example, established missionary stations and so forth. And many unexposed people suddenly contracted TB. And there's one account of this occurring in South America, and where in the first winter after these missionaries had arrived, almost half the population at that mission station actually died, and the cause of death was in fact tuberculosis. So this is reflecting sudden exposure of people who had not seen this disease forever, or their predecessors had not seen the disease for many centuries. It was Velleman, a French military surgeon, who infected rabbits with material from a human TB cavity and showed, in fact, that it was an infectious pathogen. Prior to that, many people believed, well, the scientists of the day believed that this was a genetic disorder. It could be passed on genetically. And it's not surprising, right? Because people in families who lived together got TB, right? So if there was one member of the family who got TB, it's not surprising that others had TB. And then it was in around about 1880 that Robert Koch demonstrated conclusively by actually identifying the bug, looking at it under a microscope and infecting guinea pigs and reproducing the disease, that in fact this was a causative agent of tuberculosis. And of course we still celebrate this date, the 24th of March, as World TB Day every year. That was in 1882. Of course, X-rays were then discovered at the turn of the century, and this allowed imaging of the lungs. It wasn't a conclusive test of TB, but it allowed the lungs to be imaged, and there were certain typical features which are highly suggestive of TB. Koch thought he found the cure when he isolated TB protein. So they culture up these bugs and they filter the mush that the bugs are growing in, and we call this tuberculin. And of course, some of you may know it as the tuberculin skin test. You may recall the skin test that they do for TB. And he thought, well, this would be an ideal vaccine. In fact, he gave tuberculin to people, and in fact, paradoxically, he found that TB actually got worse in some people. And that's because when the immune system is re-challenged with TB antigen, there can be a spike in an inflammatory response. And so existing sites of TB, of course, he didn't know some of these people still had active TB. In fact, many did. And in fact, it could make the disease worse. We now call that an iris or paradoxical reaction. Was there a question at the back? Or? No? Okay. Now, many of you, we then move on to sort of from about 1900 to 1950. And there was no cure for TB at the time. It was believed that fresh air, sunlight, and vitamin D could benefit TB. And the only real therapy that existed was collapsing of pulmonary cavities surgically. They called that a thoracoplasty. So they used to actually remove some of the ribs and collapse part of the chest wall, thus collapsing these holes in the lungs or cavities. I'll show you some pictures just now. And there are lots of ways you could do that. You could do it by putting balls into the chest cavity, putting air into the space between the lung lining and so forth. And it was really the only available treatment for TB. It was actually quite interesting. I think it was a French soldier who had been attacked and pierced with a sword in the chest, and the lung collapsed, and his TB actually got better. And somebody actually thought, well, this might be a good way to collapse these cavities or spaces within the lung where TB was growing. And if you collapse the lung, you collapse the space, and that allowed it allowed the immune system to access bugs in the space which were otherwise inaccessible. And then in the 1940s, there were new chemical agents that were discovered, and we'll talk a bit more about that tomorrow. There's a bit of a typo here that should read thiacetazone. However, it was soon discovered that resistance rapidly developed when only one or two agents were used, and I'm not going to talk about resistance. We'll cover that tomorrow, drug-resistant TB and how we treat it. So this is a very interesting graph, and this basically outlines to you how the mortality changed over time. This is all mortality related to tuberculosis over the years. And you can see the death rate here per million is extremely high, and over time you can see how the death rate went down. And this is in England and Wales, and very reliable data. And what is interesting, you can see that chemotherapy only came in the 40s and 50s, right? And you can see that the substantial majority, probably 90% of the mortality reduction or more, occurred prior to the advent of TB drugs. So why is it that TB rates went down? And, well, this is a very interesting question. The most important reason, I think, was the alleviation of poverty and overcrowding. And many people say TB is a social disease. It's a prime driver of TB is poverty and overcrowding. And, of course, the surrogates associated with that are poor nutrition, increased alcohol use, and so forth, and reduced immunity. It was also during this time, prior to the chemotherapeutic era, that it became recognized after the sort of late 1800s that in fact people needed to be isolated. So more and more people were taken out, put into sanatoria. There were also mass X-ray screening programs. But you can see even prior to 1880, there was quite a profound reduction in TB mortality rate, suggesting that it's really the prime driver was reduced transmission of TB and improved immunity independent of drugs. And I think we can take a leaf out of this chapter or this cartoon regarding the situation in South Africa. The only way we're really going to get on top of the TB problem is by eradicating poverty and overcrowding, and the only way we're going to do that is by building a knowledge-based economy and provision of jobs and so forth. So I don't have to explain that to you. We've got a massive burden of TB in South Africa. Although we notified about 230,000 cases, we treat roughly 500,000 cases a year. I mean, that's an extraordinary number of TB cases, and that suggests roughly that about 1% of our population has TB. Of course, that's average for the entire population, but of course, in people from previously disadvantaged backgrounds and lower socioeconomic groups, that percentage probably goes up to 3-4%, which is extraordinary. TB is far from eradicated globally. It's now the foremost infectious disease killer globally. Almost 10 million cases every year worldwide and 1.7 million deaths. 2/3 of cases are found in 8 countries. India, China, Indonesia are the top 3 because of the size of their populations, though the incidence is much lower than South Africa. South Africa is the highest per capita incidence of TB in the entire world. And the other countries are Pakistan, Nigeria, Bangladesh. Of course, South Africa makes it up there. And we have the dubious distinction of also having the highest burden of HIV globally, even by number and incidence. TB was on its way down, and then in the 80s with HIV, the TB rates went up 5-fold. So we're very good at, the power outages, we're very good at doing the impossible and achieving what nobody thought was possible. There's also a darker side of TB that wasn't enough, and that's drug-resistant TB. Here you can see in 2016, almost 500,000 estimated cases of MDR TB. This is resistance to the two main frontline TB antibiotics. And here you can see that the number actually went up last year to 600,000, in 2016 to 600,000 cases. So the absolute number of drug-resistant TB cases is going up every single year. And it's very worrying. We now have super drug-resistant strains. So there's a nice slide here. This is a paper we published in a journal called Lancet Respiratory Medicine. It's the highest ranked journal in the field of respiratory medicine. And we published this very recently. And what this described was the existence in Cape Town of super drug-resistant strains that are incurable. We just don't have, you need several antibiotics to be used together to treat TB, and we now have strains. Many of you would have heard there are new drugs to treat TB. We'll talk more about that tomorrow. But even with these new drugs, we're already having strains emerging that are resistant to many different drugs, such that you cannot put together a package of antibiotics to treat this infection effectively. And because all our hospitals are full, we're discharging these patients into the community. So I'll talk more about that tomorrow. HIV is a major driver of TB, and this is just some information about rates of TB and HIV. And this is the estimated number of people who are HIV infected and also or have TB and also HIV infected. So you can see that a good chunk, almost half of the TB cases in the country are HIV infected. And it varies in some parts of the country. For example, in KwaZulu-Natal, that percentage is much higher. At least 1 million children fall ill with tuberculosis each year, roughly represents about 10% of the total TB burden. So why do we need to worry about, yes, question?
I just wanted to ask.
Sure.
Sorry to interrupt.
No, that's fine.
Is it made worse by smoking?
Yes, it is, and I'm going to cover that in the next slide, or the next couple of slides. It is made worse by smoking, and well, it's the biggest killer of mankind. I mean, can you imagine it? Almost 1 billion people killed over the last 2 centuries. I mean, that's a scary number. TB is, you know, in the Americas, for example, and you can see, just about make out this figure here, more people were killed by TB in the US than all the wars combined, right? All the world wars combined. And as I said, it's the biggest infectious disease killer globally, amongst the top 10 causes of death globally. And if that wasn't enough, it's not just dying from TB. TB causes a lot of damage and destruction to the lungs. And even after you cure tuberculosis, there's a lot of lung damage. And people have a lot of many are respiratory cripples, right? And they have recurrent chest infections. They have damaged airways. We call that bronchiectasis. So and we don't really understand that. There's no good study about the natural history of what happens to people after TB is cured, right? That's how ignorant we are about this major problem. It's a huge concern. And so there's so many aspects to TB, and one of the aspects that's really under research, and we don't know a lot about, what happens to people after they get cured from their TB. We know that roughly 10 to 15% have very bad lung damage. They probably die much earlier than their peers, but we don't really understand that too well. We don't understand the natural history of that. So there's a lot of morbidity associated with TB, and it's got major economic consequences, right? There was a recent KPMG, not the most popular company at the moment globally or in this country, but there was a KPMG report generated about 3-4 years ago, looking at global economies. It was a rough guess estimation based on prevalent data, and it's estimated that it marginalizes the GDP of many African countries by about 2 to 3% of GDP. That's quite substantial, right? In South Africa, this equates to about almost $10 billion a year, which is over 100 billion rand per year, which is like more than half our health budget. So, TB affects economically active young people. And besides the health-related costs, you have to factor in the economic costs of young people dying, not working, the country not being developed, them not paying taxes, and so forth. So it has a substantial negative or deleterious effect on any economy. And it's quite substantial in this country. And that's something that we don't really know too much about. We don't really have a good idea what TB costs us in this country. And it's something that we are planning to work on. I'll show you tomorrow some costs related to drug-resistant TB, but we don't have a good handle on that. And I don't quite think the cabinet and the government really understands in political, economic terms what this is doing to the country. And of course, there's also substantial psychological trauma, not only with people dying and family members dying and the disability, but also when you get TB, it really affects your life, right? A lot of kids can't go to school, degrees, people stop studying, they stop pursuing their ambitions in life, and it's a very stigmatized disease. It affects the ability of people to interact with other people, even to form partnerships in life. Right, so somebody asked about smoking. So what are the risk factors? What drives TB? What fuels the TB engine? As I said, many people have referred to it as a social disease, and poverty and overcrowding is a fundamental driver, and that's a surrogate really of poor nutrition, alcohol abuse, poor income, and so forth. HIV cripples the immune system, and it makes one exquisitely sensitive to TB. It makes people 100 times more susceptible to TB. Indoor air pollution globally is a big driver of TB. So if you're cooking over wood fires and you don't have proper ventilation, you're breathing in a lot of particulate matter. And that particulate matter really stuffs up all the immune cells in the air sacs of the lung, the macrophages and the lymphocytes, and really it paralyzes them. That's the same reason why miners, right, who breathe in silica dust, the gold mines, they become very, very susceptible to TB. And many of them die from silicosis, but death is accelerated by TB because they're very susceptible to TB. So when you breathe in any particulate matter, whether it's mining dust or indoor air pollution, right? And although, electrification in this country has really progressed, I think more than 90% of the country is electrified now, and theoretically there should be very few households that should be cooking over wood fires. The reality is in the peri-urban slums. In Cape Town, you go to the Cape Flats, you see a lot of people still use wood fuel, right, to keep warm and to heat water and so forth. And we see particularly in women coming from the Eastern Cape, they have a form of lung disease. Looks like they've been smoking for 50 years, okay? So it's a form of COPD. So it's in many African countries and even on the Indian subcontinent, in South America, in China, a dominant cause, or in fact predominant cause of emphysema, if I can use that word, the old-fashioned word for and the commonest cause of COPD, in fact, is not smoking, it's indoor air pollution or biomass fuel exposure. So in fact, it's thought in terms of attributable risk that this contributes about a quarter of the total burden of TB globally is actually indoor air pollution. Smoking, somebody mentioned smoking. Smoking is an important driver of TB. Again, exposure to particulate matter. I don't know how well this projects, but this is I think, did they circulate the reading materials to you guys? No? I'm very surprised. I sent that to them months ago. Who's here from the organizers? Nobody. Oh, there we go. So I think we must circulate. Do you have got printed copies? Oh, fantastic. Okay, well, there you go. Good thing I checked on that one. But there are only 3 resources that I've listed. This is one of them. This is a review paper. It's an overview published in a journal called The Lancet. Some of you may have heard of this journal. It's quite a well-known newspaper, medical newspaper, some people call it. And in this journal, we publish this paper, which every 5 years they invite some global experts to write about tuberculosis and the latest developments. And so a couple of years ago, they invited me together with some co-authors. I put together this overview of TB, and in this you will see the fold risk of developing active TB, and you can see HIV, you've got about roughly 20 to 40-fold increased risk of developing active TB. But if you actually look at the sleeping form of TB, which I'll talk about just now, there's almost 100-fold increased risk. And you can see silicosis up there at 3 to 4-fold, kidney failure, and so forth. But this doesn't show you the attributable risk. The attributable risk is the total burden of the disease globally that's contributed by a certain factor. And in fact, if you look at the poverty and overcrowding has the highest, probably half of all TB is driven by poverty and overcrowding. I told you almost 20 to 25% by indoor air pollution. And smoking, probably about 15% of the global TB is driven by smoking, okay? And again, it's inhalation of particulate matter and paralyzing the protective immune mechanisms in the lung. All right. So why is there so much of TB in South Africa? I mean, why do we have so much of TB? Well, we have a perfect storm of factors. We've got a lot of poverty, we've got very high HIV rates, very high rates of urbanization. They say by about 2050, I can't remember the number, but about 80% of our population is going to be urbanized. And you know that we're not really keeping pace with housing or anything like that. So the so-called peri-urban shanty towns or slums are going to increase in size. And so it's not going to do tuberculosis any favors. Well, it is going to do it, tuberculosis control any favors rather. It's going to do TB a lot of favors. And of course, poor nutrition, diabetes, and so forth. And of course, there's some TB strains that come into it. Some parts of the country, like the Western Cape, have slightly more aggressive strains. So that's why we got a lot of TB in this country. And of course, if we want to tackle it, we have to address the prime driver of TB, which is poverty and overcrowding. We need to find all the HIV cases, put them on antiretrovirals or HIV antibiotics. We need to address indoor and outdoor air pollution. We need to improve housing and ventilation, decrease rates of smoking, improve nutrition. These are the really big interventions that's going to have a big effect on TB, not better diagnostics and drugs. Of course, one scientific intervention that I think will really make a huge difference is to develop an effective vaccine for TB. And tomorrow I'll talk to you about why we don't have an effective vaccine. And why is it when all other diseases like measles, we have a vaccine that's 90 to 95% effective? Why is it for TB we don't have one? We'll talk about that tomorrow. And of course, people need to be more aware of the symptoms of TB, and we need to actively go out into communities with new tools to detect TB. And I'll talk about that just now. And of course, we need to rapidly treat people who are diagnosed by so-called active case finding, and I'm going to talk to you about diagnostic strategies for TB. I don't think we'll talk about diagnosis and detection today. I'm going to talk about that tomorrow because we won't have enough time today, right? So tomorrow we'll cover diagnosis of TB, treatment of TB, including drug-resistant TB, and prevention of TB, including vaccines. Okay. All right. So what about the life cycle of TB? Humans are the only natural reservoir for TB, as I said. And as you can see from this cartoon, somebody coughs up tuberculosis bugs because of these cavities or holes in the lungs, and they enter the air sacs of the lungs. And here you can see an alveolar macrophage, which is one of the prime immune cells that will detect any dust or pollen or anything that you breathe in. And it's taken up by these macrophages and carried via the bloodstream and lymphatic channels to the lymph nodes, the mediastinal lymph nodes. And here you can see the breakdown. So there's a focus of pneumonia set up in the lungs, and you can see a granuloma there, and then that breaks down. It spreads, it breaks down, and once again TB bugs are released into the lung, and here you can see another picture of it here. Now, in fact, it's more difficult to get TB than we think. Roughly of everyone that's exposed to TB, if you're standing in a supermarket queue in Pick and Pay, I mean, everybody's walking around. Lots of people are walking around with TB, and you breathe the bugs in. Probably 80% of us will immediately get rid of the bug, right? We have the necessary defense mechanisms to zap the bug. And in about 20% of cases, we don't have that immediate mechanism. And so what happens to the remaining 20% of cases is most of those, in fact, will contain the bug, and we call that latent TB infection. It's just a bug in a hibernating state, and the bug is contained within these granulomas, which is a collection of cells. Could be anywhere in the body. Could be in the kidneys, could be in the spleen, could be in the lungs. It's a palisade of immune cells that actually contains the infection. We call that latent TB infection. And of that 20%, a small number, probably 5%, develop active disease, usually within the first year or two from exposure of disease, though in some cases, many years may pass and immunity wanes and these hibernating organisms then reactivate. So we call that reactivation TB. So all in all, of those exposed, only about 1%, right? About 1% of people actually progress to active TB over the short term. When I say short term, over 12 to 24 months, right? TB is a slow, indolent disease. It develops over weeks to months, okay? This is not something you get infected and a week or two later you become ill with TB. And so that's led to the concept of what we call the spectrum of TB infection. So in fact, we know now that this is not a isolated entity where you get latent TB or hibernating TB, and then you get active TB. It's a continuous spectrum, right? So just to show you here, this is the disease burden on this axis, and this is time. So here you can see somebody got infected with TB, and they eradicated the infection completely. They had the right type of immune mechanisms in the lung. Then you had somebody that went into the body contained the infection, and they had latent TB, okay? So this particular individual, in fact, died with latent TB. They didn't die of it, they died with it. Many of us will die with our latent TB bugs. I probably have latent infection, so do many of you. But you can see in this particular individual, there was reactivation at some point in time. Down the line, this person, for example, developed bowel cancer, and they became immunocompromised, and then the TB reactivated. Of course, the other people didn't have the necessary mechanisms to get rid of the infection or contain the TB, and so they had increasing burden of disease, and they developed progressive TB. We used to call that primary TB. It doesn't really matter anymore, because at the end of the day, we now focus on treating someone who's ill. So these old terms, reactivation and primary TB, is really fallen by the wayside. But here you can see cyclic disease, right? So you can see here, there's somebody here, they reactivate the disease, they get above this threshold where they're symptomatic and they have some cough and things, and then the immune system kind of recovers, and then several months later this may recur. And you see this in a lot of people as they appear old age. We call that chronic just chronic tuberculosis, especially in elderly people, where over time they have intermittent cough, and if you do a chest x-ray, it's abnormal. But they kind of never succumb to the disease, or they don't get rid of it either. So there's that phenotype. And so there are all sorts of combinations and permutations. And so we now have this concept, and we understand this concept of TB, where there's a hibernating state of TB bugs. That hibernating state may flux, right? There are periods when the bug load may go up and go down depending on the immune status. I didn't talk about stress, but any type of stress is also crippling to the immune system. And it's not surprising when people immigrate, often they have reactivation of their TB. It's a very stressful time in life. So I've already talked about this slide and the spectrum of TB. And here you can see hole in the lung, a cavity. You can see there's a rim of fibrous tissue in which, and this cavity is really liquefied lung. And the TB bugs thrive in this liquefactive broth, so to speak. They thrive in it because it's liquid, it's got all the nutrition, all the necessary factors they need to grow very well in a warm, dark environment, and they thrive. And that's why the cavities, that's what happens. The bug has genetically evolved to provoke quite a nasty inflammatory reaction in people, so that the human immune response actually liquefies the lungs. And this provides a nice little niche for TB bugs to grow in. And because of the very high numbers in this material, when this cavity filled with liquid communicates with an airway, that's really how the bugs are expressed. And you can see on this CT scan, you can see this cavity, and it's literally a hole in the lung. Okay, and when you get to active TB, not latent TB is asymptomatic, there's no symptoms. When you get to active tuberculosis, where the burden of bugs has progressed, the immune system fails, you start getting a pneumonia and cavities in the lungs, then these people present with persistent cough, fever, sweating at night. And that's what we call active TB. So there's two main types of TB. Active TB, you'll hear this term all the time, and latent TB. Latent TB is also known as sleeping TB, okay? And it's a state where the TB bugs are hibernating, okay? It's very interesting. We don't know too much about latent TB. There's a lot we don't know about TB. For example, we don't know what latent TB looks like in the tissues. Can you believe it? Right? We don't know what it looks like. Cannot identify it definitively. We know it exists, and we know it exists because there are many studies over time that were done over decades. And there's one very nice example in Scandinavia where they collected TB strains over many decades. And there was a young man who had TB, and his son subsequently had TB, and there was a interval of about 40 years, and they had the strains, and they could prove by genome sequencing. It's a fingerprint, genetic fingerprint, right? The same way you barcode someone's DNA and you know that they committed a crime at a crime scene. It's the same way, you can prove scientifically without doubt that it was exactly the same bug, right? So we know these bugs can linger around for many decades and then reactivate. And so we don't really know a lot about latent TB. Conceptually, from epidemiological studies and from treating people we think likely have latent TB by doing skin tests and things, we can actually show that that group has a substantially lower rate of TB. So we know it exists. We know it from epidemiological studies. We know it from genetic studies, but we can't actually prove that it's actually there and identify it. And that's one of the reasons why we cannot find a cure for TB or an effective vaccine, is we don't really know how to pinpoint some of these bugs. Now, the other concept that I want to tell you about is extrapulmonary TB. So remember, there's the sleeping TB and the active TB. The active TB can affect the lung in about 80% of cases. In about 20 to 25% of cases, the TB occurs outside the lung. We call that extrapulmonary TB. So another concept I want to introduce you to is extrapulmonary TB, means outside the lungs. And this is usually may affect, most commonly, the space between the lung and the lung lining. And when water accumulates there, we call that a pleural effusion. And it's actually outside the physical lung, but it's around the lung. That's this commonest extrapulmonary manifestation. TB can affect the heart or the heart lining, the brain and the brain lining, the lining of the abdominal cavity, the lymph nodes, and so forth. And the diagnosis of extrapulmonary TB presents a major challenge because water can accumulate around the lung for a number of reasons. Other types of pneumonias, heart failure, kidney failure, and whatnot. And when you get a patient presenting with water around the lung, you start scratching your head in South Africa. What is the cause of this? Is it TB? And then you take out some of that water, and then the problems really start, because you can't make the diagnosis of TB because the bug load in these extrapulmonary fluids is very low. Now, interestingly, there is a UCT startup exploiting a patent actually from my lab. It's called Antrim Biotech, and they've designed a test for the same-day diagnosis of extrapulmonary TB, which is about 4 to 5 times more effective than the current frontline diagnostic test. And you can Google this and read about their work, but they're about to launch this test sometime, I think it's Q1 this year, that emanates from the work done here at UCT. And UCT is one of the global leaders in TB research. We have a lot of TB, and we have a lot of people here working on TB. I already talked about why some people get TB and others don't. There must be genetic factors, but exactly how those genetic factors translate into this very specific immune pathway that protects against TB is not very well understood. Okay. The other thing we don't have is a biomarker or biosignature or a simple blood test that could tell us who's susceptible and who's not. We don't have such a test, right? We don't understand really why, even if someone who's HIV uninfected and who doesn't have diabetes, right? Like maybe a lot of your ancestors had TB, and we don't understand why they got TB. Right, so I think I mentioned this slide, and we don't understand why some people get TB. So we went back to the drawing board, and this is work being done in our lab.